Today we're talking about simulations, specifically daylight simulations. Now, I never thought I was gonna do this when I started out my channel, but I was asked in a few videos I did how I actually did my simulations. So I thought that this would be a great way of responding. Specifically because when I looked around on the internet to see what was out there, although I found some great daylight simulation tutorials, I have yet to find a tutorial that addresses why we do simulations, when we do them, and how to interpret them. And that's exactly what I want to do before actually getting into the nitty-gritty of how I do the simulations, which I'll be honest with you straight away, I'm not going to be spending a lot of time on. But nevertheless, I am going to leave some timestamps which are going to be here below, and so feel free to navigate around this video as you please. Now, with that being said, let's get into it. We always start with the climate. In this case, I'll be using my climate, which is that of Belgium, specifically Brussels. The first thing you want to look at when you look at climate is whether it's predominantly overcast or not. Now, I don't even need to tell you, I think, that the climate in Brussels is predominantly overcast, which in this case is a good thing because it lets me get away with static model simulations. Static model simulations actually don't take account the environment, the context, the climate. It's a simulation to determine how the space actually works, independently of where that space is located. It does, however, take into account its surroundings in terms of overshadowing and that kind of thing, if you model it correctly. The second thing you look at in your climate file, even when running static model simulations, is how many lux there are available. And again, I have to be specific here. You're looking at the diffuse component and not the global, which is made up of the diffused and the direct. So basically, we're looking at how much lux we're getting from our sky dome, and we're excluding the solar disk. Okay, now that we have that clear, we move on to establish a benchmark. And we have to look at the climate to establish our benchmark because we want our benchmark to be 1, realistic, which we'll get into a minute, and 2, useful. So getting back to realistic, I cannot expect in my climate, in my latitude, to be reliant on natural light for the whole 12 months of the year, 8 hours a day. That's just an unrealistic expectation which I simply cannot have for this climate. That's too bad, but it is the way it is, and it's better to know and integrate this into our designs. Now, in order for my simulations to be useful, knowing how much light I have in my environment is going to allow me to know how much light I should let in to my spaces. Does that make sense? Well, it will in a minute. We'll get into that. So before we actually benchmark, let's have a word into daylight factor, what it actually stands for. Daylight factor is, as its name suggests, the percentage of light that actually hits a certain point. So in a space, you can test several points and determine the daylight factor for each. So normally in a space next to a window, the daylight factor can be something like 20, 50% even, maybe even more. As you move inward a space, so out from that window in a side-lit room, that daylight factor is going to drop exponentially. Now that we know what we're looking for, so daylight factor, we can go back to benchmarking. Ideally, benchmarking is done before you start designing any kind of thing. And you establish this with the client. If you set your standards very high, then you will know that you're going to need more windows, better distributed, and you're going to have to make this sort of effort, and the design will reflect it. And that is why you first set a benchmark and then you simulate against this benchmark. This is what I was getting at the beginning when I said, what are we simulating for and how do we interpret our simulations? Now, the amount of lux I have in Belgium is not a lot. That's a given. So how do I work with this? In a residential project, for instance, what I would look at is what percentage of time I have X amount of lux in a given time period. I know that that sounds complicated. Just give me a minute, I'll explain. Now, if you look at the amount of light available throughout the year, you can see that 50% of the time we have 0 lux. But that's because this is taking into account the night hours as well. If we remove the nighttime hours and we account only for the hours between 8 to 5, we can now begin to see that 75% of the time we actually have 5,000 lux available. This would mean that with a daylight factor of 2%, we're gonna get 100 lux in our space. Make sense? Hope it does. We can take this even a step further and exclude the darkest months of the year, say, in this case, December and January. But that will also depend on what kind of space we're making and the benchmark we want to establish. And if we don't do this exercise, where we determine that we have anywhere between 5,000 to 7,500 lux available, then our initial premise will probably tell us that the climate is just too dark and we simply don't care about daylight because we know we just cannot depend on it, or it's going to push us into making our windows just way too big to allow for daylight to come into our spaces. When we can see, thanks to excluding those dark hours, that this is not really the case. We just saw that 75% of the time between the hours of 8 and 5, we still have 5,000 lux. That's a good starting point. Now, I hope all that made sense, so that now we can actually calculate our daylight factor in our spaces. So for that, I will move out to my computer and show you how I actually do that using my favorite design software, which is Rhinoceros by McNeil, to which I have to add a few plugins in. So Grasshopper and Ladybug. If you're not familiar with any of that and none of that makes sense and you work with other software, don't worry too much. Rhino is very powerful and is capable of opening most kinds of files. And the good news is that even if you don't have a license, it offers a 3 months free license. And even better news is that if you're a student, you can purchase the license at a discounted price, and then the license becomes professional whenever you do. So kudos for McNeil. I probably don't even need to say this, but they're definitely not sponsoring this video. They don't need to for me to say this. I love this software. I also love Grasshopper and of course Ladybug, which we're going to be using next. And those are particularly generous because those are completely free. Okay, let's dive in. Now, this is what you should see as you open up Rhino. I'm not even going to pretend like it's the same day. It's not. It's clearly not. And you can tell. I recorded this whole tutorial already, and then life happened. Everything went to... The worst thing is, it was Mr. Beast material. It was an excellent tutorial. But you're going to get an even better one. I already had a practice run. Back to it. When you open up Rhino, you should get a version of this. Before opening, however, you should follow the instructions to install Grasshopper, Ladybug, and all the peripherals that those two softwares will ask. I will link everything in the description below, and I will also leave a link in the description from where you can download my latest article on daylight, which I wrote by my lonesome without AI, and you will also access the files we're going to be creating together here on this tutorial. Now that's important because I'll be showing you something which, if you're not familiar with Grasshopper, would just do your head in, but I've made it in a way that it would be fairly easy for you to simulate anything you want. You just import the geometry in Rhino, you trace it, you place the windows, as I will show you in a minute, you connect everything to Grasshopper, you do obstructions, and you're ready to go. Let me walk you through that step by step. I will first model a 4x7 rectangle. Now I'm working on meters, but I will have everything also in the imperial system, so inches and feet, so don't worry. I'm just not going to be doing the conversions live as we do this. Now I chose 4x7 because that is representative of what I find here in Belgium, specifically in Brussels. The code in Brussels is different, and it declares that the minimum surface for a living room, dining room and kitchen altogether has to be above 28 square meters. So naturally projects are bound to this limit, and they try to keep the facades as short as possible. So 4x7 seems more or less a logical starting point. Now I'm going to extrude this, and I'm going to make it closed, so it's going to be solid, and I'm going to give it the height. The height, again, the minimum required is 2.5 meters, so that's what I'm going to put into my base case scenario here, my shoebox. Now I'm going to draw a window. Before drawing a window, what you should know is that walls have to be represented as planes. They have no thickness to them for this simulation. Okay? Now to draw the window, I'm going to go to the front view. I'm going to draw the window, which is going to be 7 square meters. Why 7? Again, this brings me back to the code. In Brussels, you need, and this is the minimum requirement, 25% window to floor ratio. So 25% of the 28 square meters we did before, that equates to 7 square meters, if my math is right. Let's do the window, 3.5 meters by 2. Now I'm going to place it in the middle of my wall, okay? That's my window. Now my window has to be in the same plane as my wall. So I'm going to move that surface I just created to the same plane of my wall. And this is how it's looking. I'm going to assume that all the other walls are going to be blind, because one is going to be the corridor serving the space or the hall or whatever, and the other two are going to be just 2 other apartments, and then top and bottom would be the ceiling and the floor. Okay? Now I'm gonna open up Grasshopper. To do that, I'm just going to type Grasshopper into the Rhino prompt. Now, when you first open up Grasshopper, it may look a bit scary. Just load up the file you downloaded for this tutorial, and you cannot drag and drop it into Grasshopper. You have to go through the file menu, go open document, and look for wherever you saved it. Daily tutorial, that sounds good. It's going to be a .gh file. As you open it, you're gonna see exactly what I want you to see. If you zoom out, it's going to look very scary. Probably it's gonna be a bit intimidating. Again, don't be intimidated. You don't have to pay attention to any of that. You just need to look into the 5 things I left for you. If you're advanced and you know how to use Rhino, you know how to use Grasshopper, then by all means, get into it. Change it as you wish. The other thing I will leave, apart from these 5 things, is I'm going to leave a slider for you, which I'm going to look for now. Now, here you have it. You have a total of 7 Grasshopper commands, which I'm going to leave for you zoomed in. So you don't need to go looking around into the Grasshopper file if you're not proficient with it. Don't worry. Now, I'm gonna walk you through these prompts. The first one is called geometry. That's your geometry that you have to load up into that space, because that's the way Grasshopper works. It's a plugin for Rhino which references shapes from Rhino and loads them into Grasshopper. Here in Grasshopper, you can change to whatever you want to them. The Rhino shape will never change. That's the basic concept. So what we're doing now is we're loading our geometry from the Rhino file into the Grasshopper file. Press left click into geometry, then right click, and you go down to set one rep. If you had pre-selected it, it's going to load automatically. Otherwise, it's going to prompt you to select it. And it's going to turn red when you don't select the Grasshopper command and green when you do. Now it's overlapping with my window surface, which is great. It's exactly what we want. Again, I'm pre-selecting the surface, and now I'm going to load it into my Grasshopper. Set one surface. Brilliant. Now I would almost be ready to run my simulation. The thing is, I have also uploaded for you an obstructions prompt. So we have to fill it, we have to give it something. So I'm just going to draw something here, a rectangle, and I'm going to extrude it. This is not going to have any impact on the simulation itself, but otherwise it would not run. If I would move this shape here, then of course it will have an impact on my simulation. I should also be drawing the context, so the floor, what's happening outside, the distance from the front neighbor, if it's relative. If it's not enormous, you should probably represent it somehow. So that's why I left this obstructions tab for you. Now we're ready to run. Depending on the size of my grid, it's going to run faster or slower. I left it at 0.25 because I'm working in meters. If I leave it at 0.25, my definition will be quite high, but my running time will be quite slow. This will be edited, so you won't see how long it takes, but it will take me about a minute and a half. No, not even a minute. The distance from the floor represents the distance at which I'm having my plane, which is measuring the daylight factor on those points. For the record, my distance now is 1. Okay, let's run the simulation. Now the simulation has finished. I can select everything here and do hide. So it hides everything and I see my simulation. Now I don't see it all too well because I have all the Grasshopper geometry, which is referenced, turned on. But I can hide that as well. I can select everything here with my left click, and then I do right click and I say preview off. And there I see my plane with my daylight simulation. Now, however, if I click here, I cannot see anything. And probably you want to be able to move it around, save it, so that you can test several iterations by moving obstacles or by moving windows. So that's why I left that final command there, which is a boolean, which is now in false. If you turn that to true, it's going to bake our Grasshopper geometry, or mesh in this case, into our Rhino. So that's true, and now we can select it, and this as well. Okay, I'm gonna erase everything now. I think that this could be helpful for you because, as I said, you can just upload anything you want, trace your geometry, and draw the windows where they are and run your own simulation. I'm gonna turn everything off and show you another example. So I'll turn off my simulation before changing anything, because if I don't, as soon as I change something, it's going to run again. To go into Rhino or Grasshopper, I just left click on one screen or the other. So now I'm in Rhino, now I'm in Grasshopper. Back to Rhino. I go to show, I see my shoebox. Let's erase this for now. Let's erase that curve. And now I'm going to show you what happens if I have, I don't know, a strange shape. Okay, let's say I have that. I'm going to extrude that. I'm going to extrude that to 3 meters now, because I don't know, it's an office building or whatever. And I'm going to have several windows now, always at the same plane. Now I'm moving and I'm pressing Alt. That's why that plus sign appears in my Rhino, because it's indicating me that it's drawing a new shape. Move it there, mirrored, have it there as well, and I'm gonna do the same windows on the other side. This is some kind of very ugly architecture, but serves a point. Now I selected all my windows and I'm gonna load them into my Grasshopper. So how am I going to do that? I'm selecting them all. I'm selecting my Windows prompt in Grasshopper with my left click. Now I'm gonna go right click there and set multiple surfaces. So all those are now windows. Now for my geometry, I'm gonna select that, select my geometry prompt in Grasshopper, and left click and right click into set one rep. I did not change my obstructions, but I can, just to show you what it affects here. And now I'm going to run my simulation. Now, the bigger the space, the longer that simulation will take, of course. Once that is done, again, I can take a look at my simulation by hiding everything. And there you have it. You can see the impact my obstruction is having on that window, and then how all the other spaces are working. And predictably, this space is quite dark. A window would ideally be needed here, unless those are corridors or whatever. But you get the idea. That's more or less how it works. And I hope this is useful for you. One more tip before leaving. You don't want your window to be touching the edge of your shape, touching the floor of your shape. You want it to be slightly above. Otherwise, it will probably not run. Again, I hope this was useful. Don't be too hard on me. This is my first time giving a tutorial. I hope I managed to transmit something to you at least, and that it wasn't too hard or too bad. I'm trying to make something which is not that easy, as simple as possible. See you in the next one.